All right, so in this video, I'll be talking about problem number 1 on the homework. And the given problem is write a finite difference approximation for p sub I plus 1 comma j for the given Gaussian equation. Now here we have a function p of t comma x. Here t is representative of time, where x is representative of space. And what we can do with the finite difference is approximate the first order partial derivative and the second order partial derivative to give us an easy numerical way to understand this PDE equation. So first, we're going to talk about notation. Let's say that this grid represents t and x, and the spacing going up and down is delta x between intersections, and the spacing going left and right between intersections is delta t. So some point in our discretized domain would be p sub I comma j. And if we wanted to go forward in time, then we can call that point p sub I plus 1 comma j. Likewise, that could be done in the delta x direction or the x direction, p sub I comma j plus 1. This is the main point behind the forward difference technique. There's also the backwards difference technique, where we'd be taking the difference between points moving backwards in I and backwards in j. There's one more technique that I want to talk about, and that is the central difference technique. And in this technique, we look at points halfway between our intersections, but the spacing between the 2 points would still be delta t or delta x if you wanted to do it in that direction as well. All right, so remember that finite difference is approximating the slope between 2 points. So here we have the definition of derivative here. And if we just take away that limit and make h a very small value, we can get an approximation of the derivative of f at x, right? So if we wanted to write that in our notation here in this Gaussian problem, we'd get something like this here. So we're approximating the slope 1 point forward in time by getting a very small delta t and taking the difference between the 2 function values. Now, if you'll notice here, you'll see that the one that I wrote down here actually already describes the left-hand side of our equation. So that part's already done. Now, let's look at the right-hand side of the equation. Here we have a second order partial derivative of p with respect to x. We can start by finding an algebraic representation of the first derivative, like so, just like we did in the t direction. And you notice that the 1 is added to j, representing movement in the x direction this time. Going back to our picture, essentially what we've done is we've solved for partial p over partial x at that point right there. If we take the backwards difference to solve for partial p, partial x, for the previous point in the x direction, we'd have the point that I just showed on the screen there. And since these points are still evaluated at the intersections, the distance between them is still delta x. Now, I did take the backwards difference here because it will make the final expression much cleaner algebraically. You can take any sort of difference that you want, and it would still work. Now, considering the 2 equations that we came up with, if we take the finite difference between them, we'd be taking a slope of a slope. And essentially what that is a second derivative. So if we algebraically manipulate this equation here at the bottom that we finally came up with, now, if you recall, we already solved for the first order partial derivative for p with respect to t on the last slide, and I'll bring that up again. Now, let's replace the PDEs in our original equation with our new approximations, and let's see what that looks like. So notice how we just substituted in our approximations here into our original equation, and this is what it looks like. Now, it's still pretty messy. So let's clean it up by leaving only p 1 point forward in time. So this p I plus 1 comma j. on the left-hand side while moving everything else to the right-hand side. And finally, here it is. So what does this equation tell us? It tells us that for any p forward in time, now remember, since any movement in the I direction indicates movement on the time axis, this is forward in time, that if we're given some initial conditions here in the parentheses, that we can find p in the future. Now, if we use tools like MATLAB, we can do this computation over and over again, giving us a model of a system, whatever it may be. This is extremely powerful in chemical engineering because our systems can be dependent on so many different factors. Anyways, I hope you found this video useful and thank you for watching.